In this lesson, we're expected to integrate the function the square root of 9 minus 4x squared dx. Once again, we'll be using inverse trigonometric substitution to do this, and as you can tell that this expression looks similar to the expression shown here, where we have the square root of a squared minus x squared. What we have to do is express these terms as either a or x. As you can tell, this 9 is the constant and this a is being squared. So I'll take this 9 and square root it, and that will serve as my a. My a will be 3. My x, on the other hand, here is accompanied by this 4. What I can do, instead of writing minus 4x squared, I can write down minus 2x to the power of 2. Notice that 2x to the power of 2 is the same thing as 4x squared. And this will serve as my x, 2x. Now what I can do is set x as the following, where I have 2x is equal to, a is 3, sine theta. And from here, I will take the derivative with respect to theta. And if I do that, I'll first divide both sides by 2, so that we've isolated for x. We have x is equal to 3 over 2. And the derivative of sine is cosine theta. Cosine theta d theta. So we just found out what we can replace dx with. It will be replaced with the following. And at the same time, we can replace 2x with 3 sine theta. But before we do that, I want to visualize what 2x is equal to 3 sine theta looks like. If we had a right triangle and we called this angle theta, sine represents opposite over hypotenuse. So if we divide both sides by 3 at this point, we would end up with 2x over 3 is equal to sine theta. This would be our opposite, and this would be our hypotenuse. So I'll put down 3 over here, and my opposite is 2x. And if I perform the Pythagorean theorem to find out my adjacent side, I should end up with the square root of 9 minus 4x squared. The square root of 9 minus 4x squared. We'll use this later in our integration. But now what I'll do is replace what I set 2x as, which is 3 sine theta, and replace dx with the derivative. We have the integral of the square root of 9 minus, and I'll take 3 sine theta, and I'll square that in a moment, and replace dx with 3 over 2 cosine theta d theta. Now our integral is exclusively in terms of theta. We'll have to change it back to x at the very end. But first, I'll take this 3 over 2 outside of my integral, and I'll distribute this 2 to both this factor and the sine theta, giving me 3 over 2, or 1.5, times the integral of 9 minus 9 sine squared theta, square rooted, cosine theta d theta. I'll factor out a 9 since both of these two terms in the radicand have a 9. We have 3 over 2. 9 being pulled out, factored out, and then square rooted gives us 3. And inside we're left with 1 minus sine squared theta, and the rest remains the way it is. Now take a look at the identity to use when we use this replacement. We have 1 minus sine squared theta is equal to cosine squared theta. So I'll replace this expression with cosine squared theta, and if you're square rooting a square, you're going to end up with the base. So we have 3 over 2, the integral of 3 cosine theta, which is cosine squared theta, d theta. I'll pull out this 3, giving us 9 over 2, the integral of cosine squared theta d theta. Finding the integral of cosine squared theta is not easy. In fact, we'll need to use half-angle formulas to do that. I do have several lessons on how to use half-angle formulas to help integrate functions, but I won't go through that again. Instead, I'll just provide what the integral of cosine squared theta is. The integral of cosine squared theta is theta over 2 plus sine 2 theta over 4. And of course, we have plus c. So I'm going to replace this part with the following. And if I do that, I'll end up with 9 over 2 bracket theta over 2 plus sine 2 theta over 4 plus c. Our last step in this integration is to replace all instances of theta with expressions of x. And to do that, we'll need to use the right triangle we constructed earlier. Notice that we can find theta in place of this theta by using this expression. If I take sine inverse of 2x over 3, I end up with theta. So sine inverse of 2x over 3 gives me theta. So I'll replace this theta with the following. But before we even do that, notice that we have sine 2 theta. Instead of using sine 2 theta, we can use the identity 2 sine theta cosine theta. That will ultimately make it easier for us when we change the expressions from theta to x. Here's what happens when we do this replacement. And by the way, I haven't switched this theta yet, as you can tell. I have 9 over 2, and by placing this expression in place of sine 2 theta, this 2 and this 4 will reduce down to half. That gives us a common denominator of 2. And on the top we have theta plus sine theta cosine theta. I can pull out this 1 over 2, factor it out. This makes the denominator out here 4, and this becomes 1. As mentioned before, I'll change this theta with sine inverse of 2x over 3 plus, let's find an expression for sine theta. That will be 2x over 3, 2x over 3, and an expression for cosine theta. For that, we'll need to use the right triangle. Cosine is adjacent over hypotenuse. Our adjacent value is this expression over 3. We have the square root of 9 minus 4x squared over 3. This is all being multiplied to 9 over 4 plus c. This represents the integral of the function we started with. And there you have it. That is how to integrate using inverse trigonometric substitution. Make sure to watch question 9 for our final question in this series.